All right, thank you everybody for joining us this morning. We're continuing on in the series of webinars about the use of artificial intelligence and machine learning in the Exabyte platform. And today, after last time when we built the classifier, we would like to extend on our results and try to make a pipeline that can do de novo generation of molecules. And James is going to explain how we can do that and how we can use Markov models to try and predict and generate new molecules. With that, James, the floor is yours.
Awesome. Thank you very much for that introduction, Timur. So before we start, let's just get this out of the way. The goal of this webinar is to really help users utilize some of the more advanced capabilities of our platform. As a result, everyone kind of should be a registered user to take full advantage of the information we're going to convey. Everyone's going to receive a PDF of this presentation, and we're going to be recording this webinar and making it available online. And then one more thing before we start, if at any point a question comes up during the webinar, please feel free to use the Zoom tools here in order to ask any questions. All right, so today we're going to start off by talking about a little bit of background information over generative models and how we can go about them. Then we'll go into actually creating our own generative model to generate a bunch of smile strings. And then finally, we'll put it all together and we'll use a generative model to actually generate a pipeline of bitter molecules. So let's go over some background. So recall that in the last webinar, what we did was we actually trained a classifier where we would feed it in a smile string, and we would featureize it using RDKit to generate several descriptors, and then we would feed this into a gradient boosted ensemble model to actually classify whether the molecule is likely to be bitter or not. It got fairly good performance on a data set where the molecules had been labeled as whether they're bitter or not. The problem, of course, being that great, we've trained a classifier on and we know the status of whether we're right or not here, but what if we want to start predicting for new molecules whether they're bitter or not? Well, there's kind of a few options that we have. Today, we're going to kind of focus on this concept of creating a discovery pipeline for that, where we made this filter in the webinar last week, and we want to find some way of generating a bunch of guesses that we can feed into this bitterness filter, which would then give us a stream of candidate bitter molecules that we could then screen further, such as with DFT or with experiment or other things of that nature. So there's a few options that we actually have for this generator out here. So one option, of course, would be to just take a data set of known molecules. They exist, things like QM9 are out there. The problem, of course, being that if we wanted to use this as our generator, kind of pulling from known molecules, the problem is that we only really have what's in the data set. And once we exhaust that data set, we're really back to where we started, where we're trying to find new candidate molecules to screen. At the other end of the spectrum, we could also try to generate all possible molecules. It would just be an exercise in graph theory, which would be comprehensive, of course, but as this paper over here shows for the GDB17 database, even if we restricted ourselves to just molecules containing carbon, nitrogen, oxygen, sulfur, or halogens, only up to 17 heavy atoms, there are still over 166 billion molecules that we would need to screen. So definitely quite a lot, maybe starting to get on the infeasible side of things. So really what we'll do is we'll kind of take a middle ground here, where we're going to be generating new molecules on the fly using a generative model, and it's going to actually resemble molecules in our data set, the one that we're going to train. So as a result, we can actually end up biasing our data set towards generating certain types of molecules based on the training set we feed in, which is a really nice side benefit to this approach. So kind of working towards generative models, we're actually going to take a little bit of an aside here and think about smile strings. So a smile string is actually a text-based representation of molecules, which is extremely convenient because there's actually quite a lot of literature out there for text generation. It's been around for quite a long time. And as a result, because we have a text representation of molecules, we can actually stand on the shoulders of giants a little bit and use generative text-based models to actually generate us new molecules. The way that smile strings work is that we have a string. Here's an example smile string for this molecule up here. We have a string of chemical symbols. These are all just chemical symbols. So nitrogen, C's here are carbons. We have a fluorine out here. It's just a bunch of chemical symbols strung together. And so that's how we get the individual symbols in here. And the way that it works is that molecule or atoms that are next to each other are considered to be connected. So walking through this molecule out here, it's actually conveniently colored based on the segment of the smile string that it's on. We start off with nitrogen, then we go up to carbon, we go to another carbon, which is this one, we go to another nitrogen, and so on. And that's how single bonds are represented in smile strings. Branches, however, because we've just reached a branch here, are actually represented as parentheses. So for example, here we have a parentheses, so we have a branch. So we go to this carbon, okay, there's a carbon. There's one more carbon, which takes us here. And then if we wanted to close this ring to make this nice heterocyclic ring out here, what we do is we can actually tag atoms with numbers. So here we've actually put a 1 after this nitrogen to say this is atom 1. And here at the end of this branch, we've specified a 1 to say the next atom is 1. What this is doing is it's letting us close this ring here. And then we're out of the parentheses and we keep going down the chain. And so that's how we can generate rings in these things. And as a result, it becomes a really flexible model or a really flexible way that we can encode a lot of nice chemical information in a text-based representation. And so definitely really worth using here. So okay, we've got now that we have a text representation of a molecule, let's start thinking about how we can actually generate new molecules. And there's quite a few options out there. One of the more well-known ones is the Generative Adversarial Network, also called a GAN. A GAN is a neural network model, and it's really two neural networks that are kind of competing against one another. That's the adversarial part. The first part is the so-called generator network. And so we can think of the generator network as something that's trying to generate sort of a fake representation of something in a data set. A classic example might be if we wanted to fake a work of art, we might have someone who's trying to generate a fake work of art from an artist. That would be the job of the generator network. We have a set of data and we're trying to generate examples that are fakes that might have come from that training set. The other part is the discriminator network. And so what the discriminator network does is it tries to detect fakes that this generator is creating. And so its score is maximized, of course, when it perfectly identifies only things that are in the training set, and it's able to always identify fakes. So this might be sort of a detective trying to figure out whether a work of art is fake or not. And these are both trained together, and over time, they both get very good at their jobs. The generator gets really good at generating, and the discriminator gets really good at detecting fakes. A very popular method. The variational autoencoder is a little bit simpler than a GAN, where it's like an autoencoder in that we have this bottleneck of information. But instead of worrying about the actual specific encoding of the molecule or of the data we're feeding in, what we try to do is we try to learn some underlying distribution that our examples are coming from. As a result, because we learn a distribution here, we can pull from this distribution to generate new smile strings in our case. And so as a result, these are actually another generative model that's fairly popular. And then there's also Markov models, and we'll actually be using Markov models today. So Markov models, in contrast to the other neural network models, they are stochastic. And what we do is we represent different states in the system, and we have lines of probability going between them. So in this example, maybe I'm at a dinner party and I'm trying to decide what I want to get from the hors d'oeuvre table. If I'm eating grapes right now, there's a probability. Here it says 10% that I'm going to go back and get some more grapes. Here it's saying there's a 40% probability that I'm going to go back and get some cheese. And I'm transitioning between states, and there's probabilities between those state transitions. And that's sort of the general idea of Markov models. We'll talk about these a little bit more because we're actually going to be using a type of Markov model. But before we do that, for any of these techniques, usually we need to figure out how we want to represent text to the machine. And so, for example, let's say I had this sentence. Let's say I'm watching a lot of Monty Python, and I have the sentence, I'd like to order spam and eggs and spam. So I can't just feed this in to one of these generative models and expect good results. I need to tokenize this first. And so tokenization is what is sort of splitting a sentence up into logical sort of units of information that are kind of displayed in a sequence. For example, in this sentence here, one logical way to do this would be to split this up by word. So here I've taken this big sentence and I've split it up so that it's just an array in memory of different words. So the first entry is I'd, the second entry is like, and so on. So this is generating something called a set of tokens. So the token is the individual word here. Next, what I can do is I can actually take these individual tokens and I can encode them in some way, because we're still not quite to something that would be easily fed into one of these models here. We need to represent these somehow. And what we're going to be doing is we might represent them ordinally. So assigning a number so that we turn this array of strings into an array of numbers. An example here would be just start at the lowest number and store the word in that slot, and just always store the word in the first slot that's not filled. For example, here the word "I'd" might be 1. We might go to like and then say, well, we've already used the number 1 up, so we'll give it a 2. And then we can just keep encoding things until we come out to something that we've seen before, which is this word "and." So over here, when I hit the word "and," the first free slot is 6. So I assign it a 6. Then we go to the word "eggs," and then we hit another "and." And we've already seen the word "and." So we can actually just say, well, this is still a 6 because we've already seen this word. Same for spam. And that's actually what we see here in this array, where we actually have encoded this sentence into a series of numbers. Here's that "and" that's repeated. Here's that spam that's repeated. We see how they're kind of pointing to those numbers here. And so this is how we can actually encode a sentence is numbers. And so then the next step would be to try to predict, given a certain number, what is the next number in the sequence. And so that's sort of how this tokenization and encoding works. So, all right, once we've tokenized and encoded, now we can start figuring out what are the states and how do I go between them. And so one way of doing this is actually a so-called Markov chain, where we enumerate all the possible states that our system can be in. A really common example is the weather. Let's really be simple and say that it can be sunny, cloudy, or rainy. And so we've got different states and probabilities going between them. For example, I live in California, so it's probably sunny outside right now. It's probably going to stay sunny, but eventually maybe there is some low probability that it eventually does become cloudy. And that probability is probably a little bit greater than the probability that it immediately starts raining. And so as a result, I could start building up a set of probabilities of transitioning between these states in California. And this is actually one way that we can actually do forecasting, for example, for the weather, and that I could actually simulate transitioning between these states over time and say, what's the probability that it's going to rain 10 days from now or something. And so this is actually one application of Markov chains would be in forecasting. And this really applies to any sequence where the current state influences the next. So things like the weather, things like the stock market, things like customer buying trends, etc. And also, text generation, of course, is one of the other big places where Markov chains have been highly successful. So, so words are actually kind of sequences, and there's probabilities that are associated between going from one word and the next. And to really drive that home, let's consider 2 phrases out here. I can either say, right, if I'm writing something, I can either say a tall mountain, or I can say a tall desert. One of these sentences doesn't really make sense. A desert can't be tall. As a result, if we kind of think about this in the context of states, if I'm in the state where I've just written the word tall, the probability that I'm going to say mountain next is higher than the probability that I'm going to say desert next. So really, English language is kind of a set of states and going between them if we wanted to do text generation. And so this is kind of the idea behind how Markov chains work. And it's actually fairly easy to write one. All that we need to do is get a corpus of text and just get a bunch of probabilities for going from one word to the next. So it is something that we could write in like an afternoon or something, but as is the case with everything else in Python, there's actually a package that someone has already written to do this for us called Markovify, which is over here. And just to kind of show off Markov chains for text generation, I've actually went to Project Gutenberg, which is a free online library of just public domain works. And I've actually taken a few classic sci-fi works of H.G. Wells, run this through a Markov chain, and I've actually generated this text out here. So these texts, I mean, at first glance, they do kind of look like they could be reasonable sentences. Usually long-term sentences with these things don't look as well. Short-term, they look a little bit better. And so this is sort of an example of kind of showing off Markov chains and how they work. And so another sort of related idea to the Markov chain, now that we're experts on Markov chains, is the hidden Markov model. And we're actually going to be using hidden Markov models today. So a hidden Markov model. So one of the main shortcomings of Markov chains is we kind of saw in some of these longer sentences out here is that over time, there's probably earlier information that has occurred in the sequence that we kind of need the context of. For example, if I start a sentence in the past tense, several words down the line, I should probably still be in past tense, which means that there's kind of, it seems like some hidden state that's influencing the outcome. It's not just the previous word that matters. Another concrete example here might be this sentence here where I have an opening parentheses out here. That doesn't make sense because I'm not in a parentheses. Why would I ever write a closing parentheses? But we can have closing parentheses in sentences. For example, here there's a closing parentheses because we were in the state of being inside of an opening parentheses. So in this example, maybe there's sort of two states in this model here, where we're either in a parentheses or we're outside of a parentheses. If we're in a parentheses, we probably can write this closing parentheses, but if we're outside of a parentheses, we're never going to put a closing parentheses. So there might be some hidden state that sort of we would want to change our distributions based on where we are in that state. Another example that's kind of thrown around a lot for this is the idea of what if we inferred the weather based on a person's activities? For example, let's say someone is calling us up every day, telling us about their day, and we want to try to guess the weather based on what they did. This is sort of another application of hidden Markov models, is trying to figure out what's some hidden state that we want to observe indirectly. So here, for example, if they tell us that they went for a walk, it's probably sunny outside. It's probably not raining. And if they went shopping, could be sunny. It could be rainy. And so what we can do with that is we can build up this idea of transitioning between these different states, but we can also do this in a generative context of just simulating transitions between states and pulling off different example things that could have happened. And so we'll actually be using one of these models for molecule generation using a smile string. Anytime that we use a hidden Markov model, however, there is the question of how many hidden states do we want to use? And generally, this requires a little bit of domain knowledge. Sometimes it's easy to infer. For example, in English, there are classically 8 parts of speech. So maybe a Markov chain predicting English sentences might have, 8 hidden states. Spoken word, let's say we were using a hidden Markov model to generate like an audio sequence of a word that sounds like a word, or an audio sequence that sounds like a word. Spoken words will typically have a beginning, a middle, and an end, where at the beginning and end in English, it's oftentimes a consonant sound, and in the center, it's usually like a vowel sound. And so there's 3 hidden states that we would include in such a model. Sometimes this is a little bit harder to infer and up for interpretation. For example, if we were trying to influence a customer's decision over time, or if we were trying to predict a customer's decision over time, the question would be, how many hidden states influence a customer's decision? It's kind of an open question that might not be easily determinable, and we would just kind of have to make a guess and see what delivered the most accurate results. And so choosing in states, definitely one of the main parameters that we can tune in a hidden Markov model. And so now that we have kind of our model, we've got a model that we want to use, we've got a corpus of data, We have the idea that we want to tokenize these strings, and we have a filter from the last webinar. Now we can kind of start going through and filling out the checklist for this pipeline here of exactly how are we going to implement these things that we just talked about. And so that really kind of brings us to the next section of this webinar, which is training a hidden Markov model for de novo smiles generation. Before we do that, however, we're going to be heavily using Jupyter Notebook in this section. And I just want to mention that we do actually offer the ability to use Jupyter Lab on our platform. Jupyter Lab, for those not familiar, is a rapid prototyping tool. It's almost like an IDE for Python, where I can type, there's like cells, I can type in Python code and get graphs and everything else. We'll see in a few slides. We can actually take advantage of our platform's compute capabilities there, including the GPU queues, which is extremely useful for GPU accelerated codes. And we actually made this easy where we've set this up already as a pre-made workflow from the curator's account on here. And here's actually how we can spin up these Jupyter notebooks and take advantage of their compute capabilities in our platform. And I'll be using this a lot later on. So here, what we can see is the user's Dropbox here. And when we start a Jupyter notebook, we actually are starting it off in the user's Dropbox so that we'll have access to anything that's in the Dropbox, just to make it easy to access, just to make it easy for users to access their data and do data science on them. Here's actually where I uploaded the bitterness classifier notebook. This is something we recorded in the last webinar. But what we can do is we can actually go ahead and create a new job because this is actually a default workflow. Here we go. So what we can do is we can actually go ahead and open up the left sidebar and we can create a new job because every account should have this already. If not, it can be accessed from the workflow bank. I can create a job, I can go to select workflow, and if I actually go ahead and search for Jupyter Notebook, I can pull out this Jupyter Notebook that's already in my account. At this point, I can give it a friendly name. I'm naming it Bittersweet Classifier because this is the one from the last webinar that we trained this in. And so then I can go ahead and go to the Compute tab, and I can actually give it the compute resources that I want. So in this case, I'm running this on AWS, and I'm giving it an instance with 16 cores, so that anything I do here is going to be run on 16 cores. And then I can go ahead and submit this job. It'll send me back to the job Explorer, and I can go ahead and run this job. And after a couple minutes, it'll start up, and I'll be able to get into my Jupyter notebook and use the resources on our cluster through Jupyter. So that's how we're going to be using compute resources for this. All right, so the data set. Remember how I said that we need a corpus of smile strings? So now that we've got our compute resources out of the way, let's think about what our corpus of text is going to be. Remember that for that H.G. Wells example, I was giving it a bunch of sci-fi books that were written by H.G. Wells and generating them for that first Markov example. Here, what we're going to do is we're going to take a corpus of quite a lot of different smile strings that have just appeared in various databases. Specifically, the user G. Lambert on GitHub has actually made this really nice molecules dataset collection where they've actually went through the trouble of collating all of these different data sets, and they've done a little bit of standardization to try to make the smile strings kind of consistently done. And as a result, we have quite a few examples of smile strings out there that we could use for this process. So we'll actually be using this data set here, and here is the link to it. I would highly recommend checking it out if anyone's looking for a bunch of chemical data to play with. The next thing up is now that we have our corpus of text, we need, of course, to read in our data set, and that's what I'm doing up here. Here, I'm just importing a bunch of stuff to make this work. Just various packages. We're going to be making these API notebooks available in our API examples GitHub repo. I didn't want to go to the next slide there. All right, and so then we can read in our corpus of smile strings. And what I'm doing here is I've just git cloned this molecule dataset collection, and inside of its latest folder is where all of the different datasets are. And here, all that I'm doing is searching for every file that ends in CSV, I go ahead and open all of those files up, and I have a set of smile strings that I'm just kind of keeping out here. I go ahead and read every smile string in the data set, and I keep adding it to the set of unique smiles if it is actually unique. And then we can just go through and see some of these smile strings that this generates. We get 10,000 smile strings out here. By the way, I'm actually dropping them if there was a colon in here. A colon in smile strings is how we represent aromaticity, and this was actually making it a little bit harder for the model to generate smile strings. So rather than tune it, we just kind of dropped it for demonstration purposes, and we still end up with quite a lot of smile strings here, about 10,000 of them, with a wide variety of chemical features here. For example, here we have dichloroethane. We have other things like carbonyls out here. It looks like we have an ester, for example, in this molecule here. So quite a few, quite a wide variety of different chemical features for our model to learn from, which is always good in our corpus, or in our text corpus, is having a diverse array of information. All right, so now we have a text corpus. Now we have to encode it. This is, again, that Monty Python example where we represented different words as numbers. Here, what I can do is I can represent different elements of the smile string as numbers. And so what we'll be using is the smiles tokenizer and encoder from DeepChem. So DeepChem is this really nice package that is sort of targeted at the physical sciences. Its stated goal is to democratize deep learning for science, and it's probably going a long way to accomplishing that. It has a lot of useful tools. It's open source. Here's its GitHub and its documentation. I would highly recommend checking it out. And it has a variety of tools to really facilitate machine learning in the sciences. It has featureizers, transformers, hyperparameter tuning frameworks, deep learning architectures, protein docking tools, and many, many other features. Today, we're actually just going to be using their Smiles tokenizer, and this is how we'll actually be doing that. So here, all right, the video is running. Before we do this, however, we actually need to quickly patch a bug in the current version of DeepChem. So if anyone tries this very soon after the June 2021 webinar, DeepChem is actually going to need to be patched. Here's the GitHub issue ticket on their GitHub where they discuss this and how to fix it. I've just written some code here to automatically patch it. And essentially what happened is that it uses the Hugging Face transformers, which are a really widely used set of transformers for language processing work. And the Hugging Face, the API for the class they're using actually changed recently. So we need to just go in and modify one of the classes out here to just be using the correct variables. And so that's what we're doing out here and why we're running this code. We'll probably remove this down the road once it gets patched in the DeepChem package. And so here we go ahead and patch that, and we can actually go ahead and tokenize our strings. Just to make things a little bit easier, I've actually written a smiles encoder object where what it does is it goes ahead, and if we don't have our vocabulary, which is just the mapping between words and numbers that we're trying to turn these smile strings into, it goes ahead and downloads them. We have this tokenizer here, which is just the smiles tokenizer from DeepChem. We have this thing called an inversion dictionary, which is this reverse mapping from how do I go from numbers to smile strings, because the DeepChem smiles tokenizer doesn't have this capability. We have to do it ourselves, but it's fairly simple to do. And then here I can just give it an ignored set of characters. We have a transform method where we can take in a list of strings, or we can take in a string, which is just the smile string, and we can return a list of integers, which is, again, this tokenized representation. And then we have this inverse transform method that I've written out here, where we take in a list of numbers representing sets of the smile string, and I get back the smile string from this list of ints. And so that's essentially what this is all doing out here. And then once I've done that, I go ahead and I create my smiles encoder, the smiles encoder object out here. And then I can go ahead and I can map the encoder's transform method over all of these smile strings that I just took in the last slide. And so then once I've done that, I can then just use NumPy to go ahead and randomize the ordering of these things, just because it's probably a good idea, just in case there is some unintended order that we have given to these things by reading them one after the other through these data sets. So, okay, so we've went ahead and we've done that. Now it's time to start thinking about how we're going to do the hidden Markov model. Because now we have our corpus, we have tokenized our corpus, and we are ready to apply some sort of a generative framework to predict new sequences based on that. So the framework we're going to be using today is actually HMM-Learn. HMM stands for Hidden Markov Model. And it's actually historically, it's called this because historically it was part of the scikit-learn package, a very well-known machine learning framework there. Just due to the diverging interests of the developers of both packages, it was actually removed in version 0.17 from scikit. Here's where that announcement can be found. And because of its where it came from, it actually follows the scikit-learn API quite well. As a result, it's interoperable with a lot of other machine learning frameworks in Python. We're not going to be taking advantage of that, but it's a very nice property to have that we can use this package and still stay in the scikit ecosystem. It's also open source. Here is its GitHub page, and here's a screenshot of its GitHub page. It's fairly actively maintained, which is always something we like to see in a package. So HMM-Learn is the package we'll be using. Next up, we need to solve the question of how many hidden states are we going to have and how are we going to train the model? And that's what we'll be doing out here. So first off, we can go ahead and tune the hidden Markov model to figure out how many hidden states should we have. In principle, this might not be the best way of doing things, but it at least takes a little bit of the decision making out of the notebook to do it this way. So here I have some objective function. I'm calling it an objective function because we want to optimize it, where I can feed it in the number of states, the number of hidden states, and all it does is it goes through and it just randomly samples from the data set, trains the hidden Markov model from that, and it records something called the log likelihood of our model, which is just a measure of how good our model is at generating new smile strings. And then it returns that log likelihood. The overall goal with this being that we want to feed in several states, record how good our model is, and choose the number of states that maximizes how good our model is. And that's essentially what we do out here, where we have a for loop here where we just go through and run those tests. We can see the one hidden state model was quite quick, but as we increase the number of states, the model slows down. So just for demonstration purposes, we're restricting ourselves to only about 4 hidden states. I'm just going to skip through to finishing up the 4th state out there. It took about a minute. And then I can go ahead and, given that I've taken the number of states out here, Matplotlib drew like 0.5 as the tick marks, but really we only have points on the integers out here. So we have 1, 2, 3, and 4 hidden states. And then we can see that our log loss improves over time, which is what we want to see. And then just to really kind of, for demonstration purposes, take a lot of the guesswork out of things, what I did is I wrote some code out here to just take the best value that we have found so far and go ahead and train a hidden Markov model using that. And the way this is going to work is this is going to keep going until our binary or until our log loss gets below 0.01, or we go through 1024 iterations. And as this trains, what this is doing is this column here is the iteration. These are iteratively trained. This column here is the log loss. We want to see this number go up, so towards 0. And then this over here, this is just how much did we change in this generation. And this is the thing that's going to eventually go to either 0.01 or we run out of time. I'm not going to go through the entire training process here because this did indeed take quite a while. Here we go, skipping ahead here. And so here we can see it ran for 227 steps until it eventually became good enough. And then we have our trained model and we save it to the disk as a pickle. Which I show up here. We train it, we save it as a pickle. So at this point, now if we think about it, we have that filter that we created in the last webinar. We have this generator for new molecule examples. So really the next thing that we might want to do is put them together. So let's talk about this generator that we've trained because I didn't really show it off in the last couple of slides. So what we've done is we've created a hidden Markov model that's going to generate us new smile strings. And so they require a little bit of processing to turn back into RDKit molecules so that we can represent them as pictures. Spoiler alert, these are the things that have been generated by our model. And so I've created this really convenient function out here where we can do a little bit of basic filtering. Of course, it needs to be a valid SMILE string. We can restrict the size of the molecules that we're generating out here. And then here's just a couple of controls to kind of have it either print what it's doing or how many SMILE strings it's allowed to check. Because if we make these too restrictive, it might never generate something that satisfies those constraints. And so that's what we're kind of doing out here is we give it these arguments and it'll generate us a set of molecules. And here's actually some drawings of molecules that it generated. For example, here we have 2-propanol, which is actually bitter. This is before we did the bitterness filtering, by the way, but this one is actually bitter. We have, I believe this is acetone. No, this is not acetone. This is 2-propanone. Don't think that's acetone. It's been a while since I've seen that structure. We have like some branched alkanes out there. We have an ether with a hydroxyl on the end of it. So definitely a lot of interesting molecules that this thing is generating. Next up, we can go ahead and prepare our filter so that we can take in the SMILE strings that our model is generating. We can go ahead and featureize them, and then we can go ahead and return the results so that we can take this, this filter and we can connect it to our generator and create a generative model, which is what we do on this slide here, where we just have a loop here where we keep generating possible bitter candidates and we just keep running until we have enough bitter candidate molecules. And so then here's a bunch of molecules that are candidates for bitterness. So out here we have, for example, this amine. We have this aldehyde out here with an amine. We have some slightly less reasonable molecules. This is probably not the best molecule out here, but we could add additional filters like for stability and whatnot. But these are all, what this has done is this has given us a pipeline of possibly bitter molecules. And then finally, just to kind of show off this live, just because I mean, I could have made these molecules and put them in the slides. So let's actually show off this thing generating molecules on the fly. And so here we see it going through and just continually trying new things. And here's molecules that it's generated out here. So again, another ether. We have this sulfur-containing species. We have this this alcohol out here. So definitely a wide variety of molecules it's generating. Then we can go through and we can take this generator. We can add a filter to it, which is what we do out here. This is just that filter that that I had in that slide. And then we can go through and just keep turning the crank until we have enough bitter molecules and we're satisfied. So these are molecules that have been generated from scratch by our model, so de novo generation. And we filtered these out using our bitterness classifier. So we have all of these out here that might be bitter according to our classifier. Yeah, and so again, a diverse array of chemical features out here. We even see a little bit of a conjugated pi bond out here, which is super interesting to see. Yeah, and so we don't actually have 2-propanol in this data set. This is actually because this is from the just running that notebook that we had, where the one that we're going to be showing online did have 2-propanol in it. But yeah, so we've generated all of these. We've generated a pipeline that can generate bitter molecules. So really the question at this point is, now what? What can we do with this tool where we have sort of a crank that we continually turn to get new bitter molecules? Well, of course, if we were interested in identifying bitter molecules, we could maybe test for binding to the protein that causes the sensation of bitterness, TAS2R. We could do this either computationally, because there are some guesses out there for what it might look like that certainly have binding sites. So maybe a docking study or something. Experimentally, maybe they're synthesized and this test is carried out. Maybe we find something more bitter than denatodium. This would also provide useful feedback for improving the filter, because we would have some means of generating a bunch of molecules, testing them and labeling them, and then putting them back in our training set for the classifier. So this branch is sort of about increasing the accuracy of our filter or just screening the candidates. Another pathway we could go down would be potentially improving the generator. There are certainly other generative models out there, like variational autoencoders and GANs, that have been highly successful in this space. VAEs have been used to generate smile strings with, for example, the All Smiles VAE. GANs have been used for this purpose as well. Another thing that we could do is we trained this on a very general corpus of molecule structures to generate this generator, or to create this generator. We could train it on a different corpus of, like, for example, bitter molecules to generate more molecules that are like those. So we could improve the generator, or we could improve the filter, or we could just go right into screening these candidates. So that's kind of what we could do next if we wanted to take this in its next steps. So that kind of ends the webinar. However, just to summarize, what we've done today is we've learned how to tokenize and encode a smile string to take advantage of these text processing applications. We've trained a Markov chain. In the intro, we showed how to train one for H.G. Wells' works. We've trained a hidden Markov model to generate new smile strings randomly, which I'm kind of illustrating with this dice game out here in the webinar's GIF. And we've actually generated new molecules and filtered them so that they have a specific properties. We've generated a pipeline of possibly bitter molecules. In the next webinar is going to be next month. The code for this webinar is going to be available on our GitHub. We're going to be doing a Q&A session in a second, but if any questions come up right afterwards, please feel free to reach out to us at info@exabyte.io, and we'd be happy to answer any questions at that time. But also, we'd be happy to answer any questions if there are any right now. Thank you.
Thank you, James. Let's see if we have any questions on the Q&A or in chat. It doesn't look like we do. Maybe we can explain how to get access to the code, just to demonstrate.
Mm-hmm.
Yeah,
certainly.
And get to GitHub there.
Oh yeah, I can go ahead and go to GitHub. All right, let's start up this. Let's create a new tab. So what we can do is we can just go to github.com/exabyte.io. And then there's actually the API examples here. It might be just /exabyte API examples. Yep. github.com/exabyte.io/exabyte API examples. And this will take us directly to the API examples where we'll be actually hosting some of these.
And the current notebook is available right now under one of the pull requests, right?
Yes, it's under one of these pull requests out here for the June webinar. Yeah, the hidden Markov model example.
Okay. Once it's reviewed, it will be available inside the other folder.
Mm-hmm. Yep, it'll be available in the examples folder under. There should be a machine learning folder in here. Maybe we haven't pulled that in yet.
It's on the others, I think.
Under others. Yes.
Not examples.
Yeah, there we go. There we go. Yeah. So under machine learning, it'll be available under machine learning.
Right. Okay, so anybody can follow and understand the code base better and run it on their own. All right. There are no other questions. I think we'll wrap up this session. And we'll see you next month. We will have a guest speaker during our webinar series. And we will be speaking about using DeepMD, the neural network framework, to understand and predict the energy landscape for structural properties. All right. Thank you very much, James. Thanks so much, everybody, who joined us today, and have a good day.
Alrighty. Thank you. Have a good one.
Bye.